So in this lecture, I will discuss weak star topology. So say that you have a Banach space M, and X is the dual space M prime, so that you have M, X, which is M prime, and M double prime. Now you consider a sequence Xn in X. Well, we have seen that Xn converge to X weakly if for all L in X prime, but X prime it's M double prime, L of Xn converge to L of X. Well, but we can embed the space M in M double prime. So if I take an element M in M, I can define Lm in M double prime such that Lm of X is equal to X of M. And now, so this is a subfamily of elements of M prime, and we could define a new topology requiring the convergence not for all bounded linear functionals in X prime, which means for all bounded linear functional in M double prime, but only for those who belong to M. So, and this will be the definition of weak star. So the definition of weak star is as follows. So assume that you have M a Banach space and that X it's equal to M prime, which is also, of course, a Banach space. Then I will say that a sequence Xn in X converge weakly star, so weak star, to X if for all bounded linear functional in M double prime, which can be expressed in this way, we have convergence. And this means that if for all M in M, Xn of M converge to X of M. So in the case in which X is actually M prime for some Banach space M, we will say that the sequence Xn converge weak star to X if for all elements M in the Banach space M, we have that Xn M converge to Xm. It's clear that this concept it's weaker than the weak convergence. So observation, weak star convergence is weaker than weak convergence. And why is that so? Because assume that you have a sequence Xn in X, Xn converging weakly to X. Well, weak convergence means that for all L in X prime, which is M double prime, we have that L of Xn converge to L of X. But this implies that for all M in M, so for all M in M, the linear functional Lm defined by this equation, so this equation defines a bounded linear functional in M prime, so an element of M double prime, Lm of Xn converge to Lm of X, but this is by definition Xn of M, and this by definition it's X of M. And therefore, xn of m is converging to x of m for all m in M, and therefore xn converge weak star to x. So we just showed that if I have a sequence converging weakly, it converges in the sense of weak star. So I just rewrote the definition of the weak star convergence. I have M a Banach space. I'm assuming that X, it's the dual of M, so it's M prime. I will say that the sequence Xn converges to X in weak star sense if for any element M in M, the sequence Xn M converges to Xm. Now, we prove that weak star is weaker than weak convergence. An observation is that if M is reflexive, which means that M double prime is equal to M, then if you converge, if a sequence Xn converges to X, weak star, so Xn X in X, then Xn converge weakly to X. And, well, this is clear because if Xn converge weak star in the sense of weak star to X, this means, by definition, that for all M in M, Xn of M converge to X of M. Now let me define Lm in M double prime as the linear, bounded linear functional which on X or on Y, so Y in X, which is M prime, it's equal to Y of M. Then, well, this is nothing but Lm of Xn converging to Lm of X. Therefore, for all such functionals, we have the convergence of Lm Xn to Lm of X. But since M is reflexive, all elements of M double prime can be represented in this way, and this means that for all L in M double prime, which is X prime, L of Xn converge to L of X, right? Because since M is reflexive, M double prime is equal to M. So we have this convergence for all Lm, so for all elements of M double prime which can be represented by an element of M, and this is the whole space. So it follows from this convergence that for all L in M double prime, which is equal to X prime, L of Xn converge to L of X, and this is exactly saying that Xn converge weakly to X. So if the space M is reflexive, then weak star convergence, it's equivalent to weak convergence. So weak star convergence, it's very much used in the context of space of measures. So let's consider the interval -1, 1. So this is an example to illustrate the use of weak star convergence. Consider the interval -1, 1, and consider the space of signed measures on -1, 1. So let me represent these measures by X. So this is not a very used notation, but just to keep the same notation of the beginning of this lecture. So let's represent a signed measure on this interval by X. And I'm assuming that, so it's a sign, so some sets, and say that this is defined on the sigma field of the Borel sets, which I'm representing by B. And it's signed, which means that some sets, some Borel sets may have negative mass, others may have positive mass. And as norm of X, I will present the total measure of X, which means that we know that a signed measure can be decomposed into a positive measure and a negative measure. So the norm of X will be the mass X plus of the interval minus 1, 1, plus X minus of minus 1, 1. So we know that X can be decomposed as the difference between two positive or non-negative measures defined on the Borel sets, which I'm representing by X plus and X minus. And I'm defining the norm of X as, well, I'm taking the measure of the interval minus 1, 1 under the X plus, under X minus, and I'm adding these two values. So here we have a normed linear space. And since we have a measure, if you consider now a sequence of measures, it will be natural to say that xn converge to x if all continuous functions in minus 1, 1, the integral of f with respect to dxn converge to f of dx. That will be a natural definition. These integrals are well defined because f is a bounded function and xn has total mass bounded. So that will be a natural topology in the space of signed measures on that interval. And actually, this topology coincides with the weak star topology. And why is that so? Because, well, consider the space, define M as the space of continuous functions in minus 1, 1, and for an element M, or maybe let me keep F. So for a continuous function in minus 1, 1, represented by F, we define the norm of F to be the sup norm. So this is the supremum of Fx for x in minus 1, 1. We have seen in a previous lecture that the dual space of M prime, it's exactly the space of signed measures. So if I represent the space of signed measure by x, so the signed measures on minus 1, 1 with this norm, we know that the dual space of this space, it's exactly, the dual space of the space of continuous function, it's exactly the space of signed measures. So we are exactly in the setup I just defined, because we know that the space of continuous function with this norm, it's a Banach space. And therefore, this convergence, it's exactly what we understand by weak star convergence. We are requiring here that xn, so an element of x, which is M prime, of f, converge to x of f for all f in M, which is for all continuous functions defined in minus 1, 1. And this is one of the main reasons to investigate weak star convergence, because it corresponds exactly to this topology I just introduced. And this example gives me also the opportunity to illustrate that sometimes weak star convergence, it's indeed weaker than the weak convergence. So I will present now a sequence xn, which is converging in the sense of weak star, but which is not converging in the weakly sense. So just remind that M is the Banach space of continuous functions taking values on R and defined on the interval -1, 1 with the infinite norm. So the dual space of M, it's M prime, which I'm representing by X, and this is a space of signed measures defined on the Borel sigma field, and the norm of these measures is the total mass of the positive part of this measure plus the total mass, so the mass of the interval -1, 1 of the negative part of the measures. Now I want to give you an example of a sequence Xn which is converging in the sense of weak star to some X, but which is not converging in the weak topology to X. And for that, well, I need to recall that M double prime, which is X prime, so the dual space of the signed measures is the space of bounded functions. And so we have shown that in a previous lecture. So now let me define a sequence Xn. So Xn will be a measure which it's absolutely continuous. So let me write this as maybe dx. So it's absolutely continuous with respect to the Lebesgue measure. And so maybe not to mix, let me call t instead of x, xn dt. And what's the density? The density xn of t will be equal to n between in the interval. So if t belongs to -1 to n 1 over 2n for n larger than 1, and it will be 0 otherwise. So we have this function takes the value n in the interval -1 over 2n, 1 over 2n, and takes the value 0 otherwise. So this is a density, and I'm defining the measure. So this is a non-negative measure, positive measure, whose total mass it's equal to 1. And what I claim, well, okay, let me define a new measure, so which I'm representing by delta 0. So this is the Dirac mass at 0. So the Dirac mass at 0, if you consider a Borel set A, this will be either 1 or 0. It is equal to 1 if 0 belongs to A, and it is 0 otherwise. So this is also a non-negative measure with finite total mass. So it's an element of our space X. And what I claim is that Xn converge in the weak star topology to delta 0. And to prove that, I have to show that for all continuous function f, Xn of f converge to delta 0 of f. So this is the integral of f with respect to Xn, and this is the integral of f with respect to delta 0. So what is the, so fix a continuous function, what is the integral of f with respect to Xn? Well, Xn is given by that. So the left-hand side, it's equal to n times the integral from -1 to n up to 2n of ft dt. And you see, since f is continuous, well, these values are very close to the value of f at 0, so it's not difficult. Well, it's very easy to show that as n converge to plus infinity, this sequence converge to f of 0, and this is exactly the integral of f with respect to delta 0, which is the Dirac mass concentrated at 0. Since this convergence holds for any continuous function, we have proved that xn converge in the weak star topology to delta 0. So we have here an example of a sequence converging in the sense of weak star to delta 0. And now, so this is the first part of my claim. The second part of my claim is that it's not true that xn converge to delta 0 in the weak topology, and that's very easy to prove. To prove that xn converge in the weak star sense to delta 0, well, we have to prove that for all element L in x prime, which is m double prime, but we know that m double prime is L infinity minus 1, 1, L of xn converge to L of delta 0. But since m double prime is L infinity, that would mean that this means that for all function f in L infinity minus 1, 1, the integral of f with respect to dxn converge to the integral of f with respect to delta 0. So this is equal to f0, and this is equal, as we have seen, to n times the integral from minus 1 divided by 2n up to 1 divided by 2n of ft dt. And now it's very easy to produce a bounded function for which this sequence does not converge to that one. Well, can take one function which is bounded and discontinuous at 0, so that won't converge. So it's very easy to produce functions, bounded functions for which this sequence does not converge to that one. And this means, therefore, that it's not true that xn converge weakly delta 0, because for that to be true, we would need this convergence to be true for all elements of m prime, and we can find one for which this is not true. So I just provided you with an example of a Banach space in which a sequence converge in the weak star topology, but does not converge in the weak topology. So let me prove 2 or 3 properties of the weak star topology. So let me start with the proposition. So M, it's a Banach space. X, it's the dual of M. And I'm considering a sequence xn in X, which is converging in the weak star topology to X. And what I claim is that the supremum, so that this sequence is bounded, so the supremum of the norm of xn, it's bounded. So there exists a finite C0 such that the supremum over n, it's of x, the norm of xn, it's bounded. And the proof, well, the proof it's very simple, and it relies on the principle of uniform boundedness. Assume that xn converge in the weak star topology to some x. By definition, this means that for all m in M, xn of M converge to x of M. But since this sequence converge to that one, this means that the supremum over n of xn of m, it's bounded by a constant which may depend on m. So for each, this means that for each m in m, the supremum over in n of xn of m, it's bounded by a constant which depends on m. So now we have a family of bounded linear functional. Remember x, it's m prime. So xn, it's a bounded linear functional. We have a sequence of bounded linear functionals whose are pointwise bounded. If I fix m, then this sequence, it's bounded for each m. And we have seen, so the principle of uniform boundedness tells me then that actually the sequence xn is bounded, so that there exists c0 such that the supremum over n of the norm of xn it's bounded. And this is exactly what we wanted to prove. So this result, which has been proved in the case of weak convergence, extends to weak star convergence. If I have a sequence xn converging in the weak star sense, then it is bounded. Then remark. So again, M, it's a Banach space. X, it's equal to M prime. And let's assume that we have a sequence xn in X such that xn it's converging in the weak star sense to X. And what I claim now, so we proved that this sequence has it's bounded. Now what I claim is that the norm of X, it's bounded by the limit imp as n goes to infinity of xn, which we proved also for the weak convergence. So let's prove that. And it's also very simple. So we have X, and we know, so X, it's an element of X, so it's a bounded linear functional. So we know that there exists an element M in M such that the norm of X, it's equal to the absolute value of X applied to M. And this element of M, we can take it as an element with norm equal to 1. So we know that there exists an element of M whose norm is equal to 1, such that the norm of X it's equal to the absolute value of xm. So the norm of X it's equal to the absolute value of xm, but xn it's converging in the weak star sense to X, so this is equal to the limit as n goes to infinity of xn m. And for each fixed n, this quantity, it's bounded by the norm of xn times the norm of m. So for each fixed n, this quantity, it's bounded by that one, which means that this limit, it's bounded by the limit imp of this sequence. But since m has norm equal to 1, this is 1, and therefore we proved that the norm of X, it's bounded by the limit imp of the sequence of norms xn. And this is exactly what we claimed. So now let me define weak star sequentially compact. So again, M, it's a Banach space. X, it's equal to M prime. I have a set C, which is a subset of X. I will say that C is weak star sequentially compact if for all sequence xn in C. There exists a subsequence x and k and a point x in C such that x and k converge in the weak star sense to x. So it's exactly the same definition of weak sequentially compact set, but now we are saying that it's weak star sequentially compact if we have a convergence in the weak star sense. And the main theorem of this lecture is as follows. Suppose that you have M, a Banach space, which is separable. Then what I claim, let me take X to be M prime. And what I claim is that if you consider the closed ball of radius 1 in X, this closed ball is weak star sequentially compact. So this is what I want to prove. If the space, the Banach space M, is separable, then the closed ball of radius 1 is weak star sequentially compact in X. So I just remind you what we are trying to prove. M is a Banach space, which I'm assuming to be separable. X, it's the dual space of M, so X it's M prime. And we are trying to prove that the closed ball of radius 1 in X, so this is subspace of X, it's weak star sequentially compact. And to prove that, this means that we have to show that whatever sequence xn in the ball of radius 1 we consider, we can find a subsequence nk and a point in this ball such that x and k converge in the weak star sense to x. So this is what we have to prove. The proof, it's quite simple. Well, we know that M it's a separable space, so there exists a subset D, which is countable and dense. So let me consider this set D, which is made of MJs. It's countable and it's dense. Now we again proceed as, well, we'll consider the Cantor method in order to find a subsequence nk. So first, let's take in step 1 M1. So we know that xn converge in the weak star sense. Sorry, xn, it's a sequence in X such that its norm, it's bounded by 1. So this means that the sequence xn m1, it's bounded by the norm of m1. So it's a bounded sequence. It's a bounded sequence of real or complex numbers, so this means that there exists a subsequence nk such that x nk of m1 converge to a limit which I will represent by a m1. Right? It's a bounded sequence of complex numbers, say, so we can extract from this sequence a subsequence which converge, and I'm representing the limit by a of m1. Now this is step 1. In step 2, I will repeat the same argument, but now with the point m2 in D and the sequence nk instead of the original sequence. So again, we have here a sequence of elements of X which has norm bounded by 1. So this means that the sequence x and k of m2, it's bounded by the norm of m2. So we have a sequence of complex numbers, say, which is bounded, and then we can extract a subsequence such that x n k prime of M2 converge to a limit which I'm representing by a M2. And I can repeat this argument for M3 and so on. And by the Cantor method, I can finally obtain, so my claim is that with the Cantor diagonal method, I can obtain a subsequence nk such that for all j, x nk mj converge to a limit a mj. So up to now, what we constructed is a subsequence nk such that for all j larger or equal than 1, the sequence x and k mj converge as k converge to infinity to a limit which I'm representing by a mj. So I wrote in this line what we just did. We obtained a subsequence nk for which for all j, this sequence x and k mj converge to a limit which is represented by a of mj. Now my claim is that for all m, x and k of m converge to some limit a of m. And to prove that this sequence converge, I will show that it's Cauchy. So for Cauchy, I will fix an epsilon, and I have to show that there exists an index k0 such that if k and l are larger than k0, then the difference between these two elements of this sequence is bounded by epsilon. So fix that epsilon. Since the sequence and fix m, so I fixed m in m, and I fixed an epsilon, I want to show that this sequence converge. So D, it's dense. So I know that there exists mj in D such that the norm of mj minus m, it's bounded by epsilon divided by 3. Now let's consider two elements, x nk m minus x n l of m. By the triangle inequality, this is bounded by x nk m minus x nk mj plus x nk mj minus x nl mj plus x nl mj minus x nl m. This is bounded, well, the first term on the right-hand side, it's bounded by the norm of x and k times the norm of m minus mj. So let me write, and I will erase. So the first term is bounded by the norm of x and k times the norm of m minus mj. The norm of x and k, it's bounded by 1 because the xn belong to the ball of radius 1. So this is bounded by 1. And by definition of mj, the norm of m minus mj, it's bounded by epsilon over 3. And the same argument applies to the last line. We have xnl instead of xnk, but it's also bounded by 1, and this is bounded by epsilon over 3. So I have that this term, it's bounded by 2 epsilon divided by 3, plus the second term, which is xnk mj minus xnl mj. Now, we know that x, nk, mj converge to a limit. So this sequence for j fixed converge to a limit. So for that fixed j, I can find a k0 such that if p, say, it's larger than k0, then x n p of mj minus amj, it's bounded by, say, epsilon divided by 6. Right, since this sequence x and k mj converge to a limit, I can find a k0 such that if p it's larger than k0, then x and p mg minus amg, the limit, it's bounded by epsilon over 6. So by introducing amg in this difference, if I take k and l larger than k0, this expression, it's also bounded by 2 times epsilon over 6, which is epsilon over 3. So I get at the end that this difference, it's bounded by epsilon, provided I take k and l larger than this k0, which depends on j, but j has been fixed. And therefore, this proves that this sequence x and k m, it's indeed Cauchy, right? If I fix an epsilon, I can find k0 0 such that for all k and l larger than this k0, this difference is bounded by epsilon. So this proves that this sequence, it's Cauchy, and therefore it converges, and I will represent the limit by a of m. And what I know, so what I claim now, is that a, well, so now a, the limit is defined for all m, right? A, it's a function from m to, say, the complex numbers. Now what I claim is that the norm of A, it's bounded by 1. And this is clear because am, if I take m in m, by definition, am is equal to the limit in k of x n k m. And this expression here, it's bounded by the norm of x and k times the norm of m. X and k, the norm of x and k, it's bounded by 1. So this proves that each of these each term, it's bounded by the norm of m, and therefore the limit, it's bounded by the norm of m. So this proves that am it's bounded by the norm of m. So up to this point, we prove that there exists a subsequence nk, such that for all m, x and k m converge to some am, and am, it's bounded by the norm of m. Now what I claim is that A, it's linear, so now what I claim is that A of m1 plus m2, it's equal to A m1 plus A m2, and that A alpha m, it's equal to alpha am, so that A is linear. And this is clear because A, let's say, let me prove the first line, A m1 plus m2, by definition, is the limit of x and k m1 plus m2. But x and k, it's an element of x, which is m prime. So x and k, for each k, it's a bounded linear functional. So x and k of m1 plus m2, it's equal to x and k of m1 plus x and k of m2. And therefore, am1 plus m2, it's the limit of x and k m1 plus x and k m2. But by this relation, this is am1 plus am2, which proves the first line. The second line, it's proved in the same way. So we have that A defined by this equation is linear, and it's bounded. So A, it's an element of m prime, which is x. So A, it's a bounded linear functional on M. And furthermore, A of M, it's bounded by M. So this means that this element of M prime has a norm bounded by 1. So A belongs actually to the ball of radius 1, the closed ball of radius 1 of X. And furthermore, X and K of any M converge to A of M. So X and K of M converge to A of M for any M. And this is exactly what weak star convergence mean. So we proved that this sequence X and K converge to A in the weak star stance. So this implies that X and K converge in the weak star sense to A, and A, it's an element of the closed ball of radius 1. So we proved exactly what we wanted. There exists an element of the closed ball of radius 1 and a subsequence nk such that X and K converge in the sense of weak star to X, where X is equal to A. And this completes the proof of this theorem and this lecture.